let me start the second part of my talk, my lecture. So I'm going to focusing on the numerical algorithm for the eigenvalue problem. Okay, so the first part, first we should start the mathematical notation. So I always use the capital A. Yes. So this is always a matrix to be diagonalized, or we solve the eigen problem. So sometimes it is a real matrix, but yeah, so it depends on the application or target problem. So sometimes the component or the elements, the complex number. So either we choose the properties, real or the complex. And the number of rows and the number of the columns. So row and column often differ the variable m and n. So m by n. So this is the manner of the very basic standard software BLAS notification rule. It is a rule. So if I use parameter or variable m, so it is number of rows and also number of columns, always n. So it's equal to n. And so the matrix is transpose, or its transposition is also the same or identical. So we say that it is a transpose matrix, or if there's the matrix is a transpose and a conjugate, so it is the same matrix. So we say that's Hermite matrix or Hermitian. So this material science lecture, so we will deal with either transposed or Hermite matrix. Okay, so the solving the eigenvalue problem or the eigenvalue solver, so matrix should be a squared shape, so n by n. Otherwise, we cannot solve the eigen problem. We need to use another mathematical framework, the singularity decomposition. So in the case of the squared matrix, so we use eigenvalue analysis. Okay, so consider this relation. So if we have the certain vector, it is a non-trivial zero metric, zero vector, and so one scalar, ax equals lambda x. If we have such a relation matrix A, x is, I'm sorry, so first lambda, so scalar lambda, it is the eigenvalue of matrix A, and so x is the corresponding eigenvector to the eigenvalue lambda. It is also the we have another relation or another formulations like A minus lambda I. So capital I is we use the trivial formulation of the identical identity matrix. So just only the diagonal is diagonal part 1, and otherwise other matrix elements are 0. Then so A minus lambda I, and so multiply the vector x. So it shows well, it's returned the result in the 0 vector. So in a relationship, so we have lambda and x. They are the solution of the eigenvalue problem of the matrix A. But here, so we can say if this relation, so x should be also 0. But so if we have a non-trivial, so non-zero vector, so it is the eigenvalue and the eigenvector. Okay, so and also this relation, so it is sort of mathematically, so we have sort of the same the feature defined by the sort of matrix determinant. So like sort of A minus lambda I, it's a determinant equals 0. Yeah, this relation is also defined as sort of the matrix eigenvalue of the sort of matrix A. If the lambda it is the parameter, so if you have sort of appropriate or a certain value, so lambda, and so it's satisfied sort of this determinant equals 0, so lambda is the eigenvalue. Here, so we don't have sort of any x, but we can input the sort of lambda into this relation and sort of find the sort of the eigenvector x. Okay, so this is a sort of definition, mathematical definition of the sort of eigenvalue, eigenvectors. Okay, so generally, the determinant. Okay, so yes, the last equation. So this can we can extract this matrix formula into the sort of very simple sort of polynomial format. So because sort of it is expanded to the sort of nth order polynomial. So so second order polynomials, so we have sort of two roots of the polynomial. Third order, so we have three. So it depends on the sort of the order of the polynomial. So now, so we have sort of nth order. So we expect sort of n different, but or we should consider sort of algorithm. Algebraic sort of duplicatory for the sort of the roots. But if we consider sort of any duplication, so exact n so roots are expected. So okay, so now if we fix the sort of matrix or format as a symmetric case, or emit the order eigenvalues are real number. This is true because we can easily to confirm sort of these relations. Okay, so we have a sort of an inner product of x and ax because x is sort of already known as a sort of eigenvalue of the corresponding to the sort of x is the eigenvector and this is corresponding to the eigenvalue of lambda. So ax should be the sort of lambda x. And the scalar can be the sort of right hand side, so it is a sort of straightforward to extract in this port outside. And also we have another exchange of sort of first and the second term with the sort of conjugate operation. So I'm sorry. So we use the sort of I use the sort of h as a sort of conjugate transform. So h x and x. This is also ax because now we suppose sort of A is a Hermitian, so A conjugate transpose should be sort of A. And then so AX is a lambda x, and from the left hand side, the scalar is yes. So we can so extract sort of this term with the sort of the conjugate of the sort of scalar part operation. So we have lambda XX and the lambda bar XX. So these are equivalent. So lambda and the lambda bar, they are same. So such a number is always a real number. So if the sort of matrix is symmetric or Hermitian, so we always obtain the sort of real eigenvalues. Eigenvalues. Okay, so corresponding eigenvectors are sorted in a diagonal matrix of the lambda. Okay, so now we only consider the single value of the eigenvalue. But if now here, so we have n eigenvalues. If we solve the sort of all possible eigenvalues, so we sort the sort of possible lambda into the sort of diagonal part of the sort of matrix lambda, capital lambda, and the sort of all the corresponding sort of eigenvector into the sort of capital X. So we have AX equal X lambda, like that. This is another the formulation of the eigenvalue problem. But also we sometimes say that this is a eigenvalue decomposition. So because matrix A can be decomposed by the something of the matrix multiplication. Okay. So, oops, I'm sorry. Okay, so now we have another very significant or the important feature of the eigenvector or the sorted the matrix capital X. So the capital X, so it has a very significant feature of the also normalized feature. So if we compute the X and the X transpose, I'm sorry. So if we, which I should use H. Okay, so now this notification, this presentation should be symmetric. So if we use Hermitian matrix, I should use H or XX transpose or XX conjugate transpose. And also the another order, X transpose X or X conjugate transpose and X. They should be identity matrix. Let's say any eigenvectors and another tag. If we choose another eigenvector, so always they are orthogonalized. And also the norm is also normalized. If we calculate the eigenvector norm, so we can say we can take always one normalized eigenvector. Okay, so last slide. So I used this notation AX equal X lambda, but multiplies the X transform or the X conjugate transform from the left hand side. We have such a formulation X transpose AX equal lambda. So this operation, so we compute the capital X and the capital lambda and multiply the X and X transpose from the left and right hand side of the matrix X. So we can obtain the eventually the diagonal matrix. So this operation, so we say that diagonalization of the matrix A. So sometimes we say that sort of solving a sort of eigenvalue problem, so as eigenvalue decomposition. So this is a sort of diagonalization. Yes. Okay, so eigenvalue decomposition. So the EVD, so this is a sort of very core mathematical operation in the sort of material science. Okay, just I want to say that sort of if matrix is not symmetric or Hermitian, so eigenvalue so should be a sort of complex number. So as I showed, sort of the characteristic equation that is a sort of extracted or expanded from the sort of determinant of the original definition of the eigenvalue problem. It says sort of always, no, not always. In most cases, root of the polynomial should be a sort of complex number. So the symmetric and the Hermitian, so these are the very exceptional case. So the general case, so we should consider the complex number if we need to treat the sort of eigenvalue problem. And also, it's difficult to find a sort of very significant feature of the sort of eigenvectors, X transpose X. They are not usually sort of identity matrix. They don't have any general feature, how to say. So we should use the different formulation if you want to use, or if you want to introduce the matrix, a similar type of the matrix decomposition. So A, Y, because X is already used for sort of eigenvector, so use sort of different notation. So Y equals Y J. So if you already learned something sort of Jordan format, Jordan form, so this is a sort of the yes, applicable to the sort of Jordan form here. Okay. So from here, so just apart from sort of mathematical, the definition of the mathematical treatment, just so moving forward to the sort of numerical sort of treatment. Okay, so how we can solve the sort of eigen pairs. So here, pair means the sort of eigenvalue and the sort of eigenvectors. So yeah, so maybe so you understood the sort of eigenvalue problem, eigenvalue decomposition. This is strictly sort of defined by the sort of the matrix determinant. So the polynomial, so it is a sort of very origin. So somehow, so we can solve the sort of eigenvalue, and then so we need to solve, or we need to calculate the eigenvector. So the step should be or a possibility. I can list up the three types. So first, we only solve the sort of we solve the sort of nth order the polynomial. Then eigenvector can be solved as a sort of kernel base of the sort of A minus lambda I. But solving the sort of kernel base, it is also very, how to say, difficult operation. So yeah. So we can use the sort of different type of the sort of numerical algorithm. Okay, so second one is a sort of very, I think this is a general. So the numerical algorithm, which leverages the sort of numerical feature, unbalanced the sort of growing factor among the sort of large and the small the eigenvalues. Okay, I will show the sort of this technique to the sort of next slide. And so third one, it is a very special technique or explanation. So the very special the sorting the algorithm and the mechanism. I think the third one, it is something engineering technique to find sort of eigenvalue, eigenvector for the sparse matrix or the sparse iterative or the numerical sort of method. My lecture, so it is going to focus on the dense eigenproblem. So the second one, so it is the main mechanism or the main counterpart to solve the eigenvalue problem. Okay, so okay, so now I want to show the sort of algorithm chart. We have now the eigenvalue problem to be solved. So AX equal lambda X. But we don't have any almighty or the perfect algorithm to solve any matrix and any eigenvalue problems requests. So here, we can divide or introduce the two cases for the sort of matrix. If the matrix is dense, here dense means the matrix element n by n. So they are non-zero elements as almost. But the sparse, for example, the only diagonal or off diagonal or some matrix, it has a sort of a structured case and non-zero term, almost zero, but it's a non-zero terms. There is how to say 10%, 20% non-zero elements included for A. That's case we say the sort of sparse matrix. Okay, so now, we just only focused on the sort of dense case. So this time, we try to deal with the symmetric or Hermite. But other cases, asymmetric or non-Hermite. Focusing on the sort of symmetric Hermite. So if we only solve the sort of largest or smallest eigenvalue. For the scientific simulation, for the purpose of the sort of solving the sort of very stable or very secure the state, so largest or smallest. So this kind of sort of eigenvalue problem, very limited. The case is sort of very general. So that's case. So we use power method or inverse iteration. Or eigenvalue or eigenvector. So numerically, we use the different algorithm. I will not explain this algorithm, but bisection or inverse iteration. So they are very familiar in the sort of numerical linear algebra community or HPC users. Okay, so another case, all eigenvalue and eigenvectors pair. So QR iteration. I will show this algorithm later. And if we use, if we need to solve a very huge matrix, or we need to use access to the parallel computer system. So the parallel algorithm, like this combination, household tridiagonalization and the bisection inverse iteration, they are also used for the modern numerical library, like iSpark, RayPark, and so my library eigenx. Okay, so the state of the art, so eigenvalue solver, they are using sort of very special algorithm for solving the sort of very special matrix. So these are feasible for sort of matrix parallel computer system, or it's shows a very nice performance or the nice accuracy for the specific problem. So the library or software package, so they select the internally the appropriate algorithm. But this time, so I just only show the very fundamental the technique, this one, the power method and the QR iteration in this lecture, and the sort of hands-on or after lunch break. Okay, so first, very basic algorithm, the power method. This is for we used this algorithm for solving the largest eigen value and its corresponding the eigenvector pair. Okay, so this algorithm is very, very easy. Just only to multiply the matrix to the sort of vector the many times. Of course, we need to introduce several additional operations, so like normalization. But if so condition like the largest eigenvalues, so it is only identical one, only the single eigenvalues are existing, so not duplicated. So in this case, we mathematically, so we can guarantee this process converges to the largest eigenvalue. Here, largest it's meaning the only the positive number, so it includes negative. So we should consider absolutes, the value of the eigenvalues. Okay, so. Okay, so this is a very simple example. So 2 by 2 matrix, the diagonal so parts the 1 and the off diagonal so negative 1, and we choose the initial vector. So like this, we don't need normalization, so 1, 2, so component elements we can choose very simple one, but so eigenvector we obtain should be also normalized, so input the initial guess, so it is also the normalized like that. Okay, so A and the initial guess x0, we compute A x0, and we substitute the A x0. Then normalized one is substituted, so the x1. So this is the x0, and multiply the A from the x0, and so the normalize its norm like this, and this is x1 minus 1 over the square root 2. This is also x1, and also again multiply the A from the left-hand side, the x1, but we obtain the same vector, x1, x2, they are same. So we stop here. Then compute x2 and inner product of the x2 and the ax2. So we obtain 1 So this is a sort of absolute value of the sort of largest eigenvalue. So we should check the sort of the sign. It is a negative or a positive. No, I'm sorry. So this sign is true. So if we multiply the sort of a, multiply the a and the sort of x2, so it is well, to say it's multiplied the same. So it shows sort of 2, 1. I think it is correct. Yes, yeah. 1, 2, multiply this -1 plus -1. So let's say this 1 and 1. Oops. Oh, is it correct? I think it should be sort of 2 or something. Okay. Yeah, please confirm this is it is correct. Sorry. So when I prepared sort of this example, sort of eigenvalue should be 0 and 2. So this should be this should be 2. Okay. So eigenvalue, if he computes the sort of largest one, so it return this algorithm returns 2, and the eigenvalue, eigenvector. So eigenvector should be then, and the sort of eigenvalues the 2. Okay, so this is a sort of very simple, just only sort of multiply, and with the carelessness, so we can obtain a sort of correct eigenvalue. I'm sorry, so we should please confirm this. This is a very, very simple algorithm to obtain the sort of largest eigenvalue. But we are not sure in the internal principle. So why is this process, iterative process, converges the largest, absolutely is the largest eigenvalue. So this is just a brief proof. We eventually get the largest eigenvalue. So the first, so we assume we have such as an assumption. So lambda, okay, eigenvalues. So we consider the absolute value of the eigenvalues. They are identical and separately existing, and lambda 1, this is the sort of largest. So I mean the sort of sorting a sort of descending order. And we introduced a special the parameter, so lambda I dash, it is divided by the sort of absolute value of the lambda 1, so largest eigenvalues. And suppose the sort of alpha 1 variable, the parameter, that it should be so larger than 0, not non-zero. And then define the sort of sub function like that, and iterate the matrix vector multiplication like that. So the x0, so initial guess, if we have a strict or the exact eigenvalue decomposition, so like x0, eigenvalue lambda something, and also the eigenvector corresponding eigenvector x something. In that case, because any vector can expand by the sort of combination, linear combination of the sort of eigenvector. So we can represent the sort of x0 as like that. But we should normalize the x0. So the c0, yes, we need to introduce like that. And the multiplier is sort of a, the x0. We have like that, and the c1, it should be a sort of normalizing factor. It is calculated like that, and we have x2, x3, and so general case xk like that. k times multiplied as the a consecutively to the x0, or we have like that. Now we have lambda dash term like this. Lambda dash, it is defined by like this. Lambda 1 is always largest one. So lambda I dash, this should be less than 1. If we choose k as the very huge number or going to the infinity, this value, so this vector, so it is going to converge like that, x1. Only this term is remaining, so this term is diminished. And fk, it is also converged to the alpha 1. So cancellation, so alpha 1, alpha 1. So converge to x1. So that's why we obtained a certain vector. And so if we compute some ratio, so it is associated with the largest eigenvalues. So this is a very brief story. Why the power methods it is utilized for finding the largest eigenvalues. Though the power method, it is a very simple one, but we should confirm the sign. We only obtain the absolute value of the largest eigenvalue. So we should check the sign, positive or negative, in the final step. And also, maybe a hands-on session. So we will do some demonstration of the power method. But maybe you will feel the convergence speed. It is very slow sometimes. Of course, we choose appropriate the initial guess. It converges just only to 1 or 3 iterations. But if we choose a larger matrix, like also 10 by 10 or 100 by 100. So power method, it shows a very slow behavior of the convergence. You can see the previous page. So convergence, so it depends on the distance. So if we vanish these vanish very quickly, so we don't need any larger number of the iteration. So it depends on this value. So the largest lambda dash, it comes from the ratio between the largest and the second largest the eigenvalues. So if we have almost the same eigenvalue in the largest and the second largest, so power method, yeah, it doesn't converge. We need 1,000 times the iteration. Okay, so I said this power method, it is aimed to solve the largest eigenvalue. So, but if we have something the way to solve the inverse, matrix inverse, or solve the linear system, so we can solve the specific eigenvalue or nearest nearest value to the specific date value. So it is a special version or the modification of the power method. Using this inverse notation, so the power method, so it is applicable to any value of any eigenvalues or computation. So if you set lambda equals 0, so power method, and its inversion, provides the smallest eigenvalues. But yeah, maybe you know, so the matrix inversion, so it is a very costly numerical operation. So yeah, we use the another approach to solve this, not yeah, so solving the eigenmode, not only the largest one.